everyone. You all are welcome to the lecture 8 of module 1 in the course Information and Communication Theory. In this lecture, we are going to discuss functions of two random variables. First, we will discuss one function of two random variables. Then we will discuss two functions of two random variables. And in two functions of two random variables, we will try to find out their joint distribution. So in order to achieve that, let us first try to understand what may be the joint distribution of two random variables. Here the two random variables considered are x and y, and its joint CDF is represented as fxy where these xy's are the random variables and this x and this y is their respective highest possible value that those random variable can take. In short, it is represented as fxy. So this x is not the random variable x, this s is the highest value that random variable x can take, that is this x. So fxy actual definition will be probability random variable x less than equals to x and random variable y less than equals to y. Means x is the highest possible value that can be taken by this random variable x. This y is the highest possible value that can be taken by this random variable y. So their probability will be the joint CDF of the random variable x and y, and this probability is actually written as probability of xy such that xy belongs to region D1, where D1 region will be defined for those two values of x and y, and this region D1 will be clear later on. We will consider four examples. The first example, probability xy belongs to D1 means if we consider this plot, we have horizontal axis as x-axis, vertical axis as y-axis. In general, let us say this is point x, this is point y. So for xy belongs to D1 means this shaded region will be represented by D1. So this probability actually means we are calculating the sum of probabilities of all the possible outcomes for which the random variable assigned falls into this shaded region. Consider second scenario where we need to find out probability such that random variable takes the values between x1 and x2 and random variable y is less than equals to y. This probability is actually written in terms of CDF as fx2y minus fx1y. This we have already discussed. The actual meaning of this is fx2y means this, let us say this is the value of y, this one, and x2 is this value, x1 is this value. Then fx2y means left hand side of this line up to minus infinity. fx1y means left hand side of this line up to minus infinity. So if we subtract fx1y from fx2y, we will left with this region. So this region actually defines the region D for this probability. Similarly, if we consider probability x less than equals to x, but y is allowed to take values between y1 and y2, that by definition will become equals to fxy2 minus fxy1. So if we consider this point as x, so this line will correspond to x, this point is y2, this point is y1. So fxy2 means below this line up to minus infinity, and fxy1 means below this line up to minus infinity, and this goes up to minus infinity also in this direction. So their subtraction or their difference is this shaded area. So this shaded area will there be represent the region of interest T for calculation of this probability. The last example, let us consider x is allowed to take value between x1 x2, y is allowed to take value between y1 and y2. If we solve this probability, we will get this expression fx2 y2 minus fx2 y1 plus fx1 y1 minus fx1 y2. And if you express these probability in the region or these distribution function in the region, you will get this as the region of rectangle as the region of interest for calculating this probability. We are discussing the representation of probability in terms of region because this concept will be going to have extensive use when we try to find out the joint distribution for two random variables. Based on joint CDF, we can easily determine the joint PDF fxy as second order derivative of joint CDF with respect to variable x and y. Similarly, we can say that joint CDF will be equals to double integral of joint PDF with respect to variable alpha and beta, where alpha is allowed between minus infinity to x and beta is allowed between minus infinity to y. Now there is another scenario. If we have two random variables and both random variables are independent to each other, that is they fall into the category of independent random variable, then their joint CDF fxy will equals to multiplication of individual CDF fxx into fyy, and similarly their joint PDF will be equals to multiplication of individual PDFs, but this is valid only when x and y random variable are independent random variable. Now let us consider the first scenario where we have two random variables x and y, and we generate another random variable z as a function of these two random variable, and functional behavior is given as gxy. So the third random variable z is actually g of xy, where x and y are two random variables. Let us say we have the information about joint distribution of these two random variables of x and y. From this information fxy xy and given the functional behavior, if we have been asked to find out what may be the distribution of third random variable z. So this is the task we need to perform in this lecture. Now there is one example. If suppose you are applying a input signal as x to any active circuit and y is the noise generated inside that active circuit, then at the output of the active circuit you will get z as the x plus y. So x is treated as first random variable applied as input, y is the second random variable generated as noise inside the system, then z is the third random variable that is available at the output of receiver or the active device. So this is just one example that in practical scenario we may encounter with the random variable which is actually depending on two or more random variables. Now this particular figure gives you some example that what may be the nature of gxy, the function gxy. Function gxy may be sum of the two random variable, difference of the random variable, multiplication, division of the random variable, or some other type, that is max min of two random variable, root x square plus y square tan inverse x by y or y by x. But this is just some example. There are infinite possibility of random variable function gxy that can be used to generate another random variable. Now coming to the case of a random variable generated z using functional behavior g and two random variables x and y. So we can say that random variable associated with the experiment zeta, which is equals to z, is given as g of xy. Then CDF of this new random variable z, which will be represented as fzz, equals to, by definition, probability z zeta less than equals to z. This z is the random variable, this zeta is the outcome, so we are actually assigning a number to each possible outcome, and if the number assigned to each possible outcome of an event is less than equals to z, a particular value, and if you try to find out probability of this event, then that will be called as CDF of that random variable fzz. So simply substituting the expression of z in terms of gxy, we will get this probability as probability gxy less than equals to z. We can also say that this is the probability of xy, where xy is belong to the region dz, or we can say that region dz is a region in xy plane where this condition gxy less than equals to z is satisfied. So we can say that the region dz contain all the coordinates of xy such that those coordinates will comes from the solution of this function. So if we solve this function to get the different values of set xy for particular z, and if we combine all those solution or all those points, we will get the region dz. This can also be written as, since there are two variables x and y, so double integral of PDF with respect to dx dy such that x and y belongs to that region of interest dz. So this particular concept will be utilized in this lecture. For an example, let us consider the random variable z is given as x square plus y square, which is generated by the two random variables x and y, and we have been asked to determine its distribution fzz or capital Fzz. If we determine fzz and integrate with respect to dz, we can get the small fzz. For CDF, fzz will equals to probability z less than z, that is probability x square plus y square less than z, that is double integral of joint PDF of xy with respect to x and y variable for the region where x square plus y square is less than equals to z. So we need to integrate this PDF only for this region where x square plus y square is less than equals to z. This can be written as, if we consider this line, x square plus y square equals to z will represent this circle, and x square plus y square less than equals to z means inner side of this circle. So if we consider only this line is the y axis, means x equals to 0. So this line is extending from y equals to minus root z to y equals to plus root z. So this will be the limit of this integration, and once this line is allowed to vary this side and this side, we will cover the entire circle provided x square plus y square is less than equals to z. So that will be give the limits of x as x minus under root z minus y square, x equals to under root z minus y square. So if we integrate joint PDF for this region or for these limits of x and y, we can easily calculate its cumulative distribution function of random variable z, and if we differentiate it, we will get PDF of random variable z. Now let us move to slightly complex scenario where we have two random variables x and y, and it is used to generate two different random variables z and w. So if we use the two random variable x and y along with functional behavior g in order to generate z. Then we will use the same random variable x and y but with different functional behavior h to generate another random variable w. So z and w are two random variables generated by x and y random variable but with different functional behavior g and h respectively. So if this is the scenario and we have the information about joint CDF or joint PDF of x and y random variable, then the question is how we can determine the joint PDF of the two new random variable z and w, which is represented as fzw, zw. For this, first let us consider the joint CDF of two random variable fzw, which will be defined as probability z zeta is less than equals to z and w zeta is less than equals to w, or we can say probability gxy for z zeta is less than equals to z and hxy for w zeta less than equals to w, which is equivalent as probability of xy such that xy belongs to the region dzw. Now dzw is a region in xy plane, just remember xy plane, not the zw plane, but dzw is the region in xy plane where inequalities gxy less than equals to z and hxy less than equals to w will satisfy simultaneously. So whenever we have that region, we can say whatever is the probability of coordinates xy falling into that region, that will be the probability equivalent to probability gxy less than equals to z, hxy less than equals to w, or that will be the CDF of joint distribution zw. So this probability can be evaluated as again double integral of joint PDF of xy random variable with respect to x and y variables for the region where xy belongs to dzw. Now again, let us elaborate this discussion to come out with a mathematical relation or mathematical formula where we wish to determine fzw in terms of fxy. For this, let us again consider the random variable z equals to gxy and w equals to hxy, and these two functions g and h gives us many solution or many possibility in terms of x and y for a given z and w. So those solution, let us say, represented in terms of xi and yi. So we will get z as g of xi yi and w equals to h xi yi. So for a particular z and particular w, it gives many solution in terms of x and y, where those many solution will be indexed by variable I. Now consider the probability that a random variable z takes any value between z to z plus delta z and random variable w will take any value between w to w plus delta w. What it means, the random variable z and w will falls into the region delta z and delta w. This will be clear in this expression, but coming right now here, we simply substitute the expression of z and w in terms of x and y. We will get this expression. Now we can easily determine the joint distribution of fzw provided these two functions gxy and xy are continuous function as well as they are differentiable function, means their differentiation exists. So if these two constraints will be satisfied by these two functions, then we can easily determine the joint distribution of z and w. Now let us say gxy and hxy is given in such a manner that these two constraints are satisfied. For that scenario, we will have this probability that z is allowed to take value between z to z plus delta z, and w is allowed to take value between w to w plus delta w, it is equivalent as probability zw belongs to the area or the region delta z into delta w. This can be equivalent as FZW, that is the PDF of ZW, multiplied by the area of delta Z delta W. Here integration is not used because the delta Z delta W area is considered as infinitesimal area. If it is a finite area, means significant area, then we need to double integrate this FZW with respect to dz and dw. But since this area is infinitesimal, so we can approximate this probability as PDF multiplied by that infinitesimal area. Now, in this expression or the above expression, we have seen that this probability was PDF multiplied by this area delta Z delta W. So let us consider that delta Z delta W area in JW plane is equivalent as an area delta I in XY plane, or we can say probability ZW belongs to delta Z delta W is equivalent to summation over I probability XI YI, here is XI YI belongs to delta I. Why the summation is used here? Because for a given Z and W, there are many possible solution exist in X and Y. So for a given Z and W probability, we are clubbing all those possible probabilities of those solutions. So because of this reason, summation over I is used. So summation over I probability xi y belongs to delta I. This is equivalent to fact that this will be summation over I fxy xi yi, that is the PDF of random variable x and y, multiplied by delta I region or delta I area. So next, if we compare this expression which was equals to this one and this same expression which is equals to this one, we will get the expression fzw, that is the PDF of random variable zw, equals to summation over I joint PDF of xy multiplied by delta I divided by this delta z into delta w. So in this expression, we want to determine this quantity, that is the left hand side. We have given this quantity in right hand side, means if we able to determine this ratio delta I by del z into del w, then we can easily determine fzw in terms of fxy. So let us now proceed how we can determine this ratio. For this, let us consider that joint PDF of random variable zw will be equals to summation over I f joint PDF of xy multiplied by determinant of Jacobian JZW. It means we are representing this ratio delta I by delta Z delta W by this new quantity determinant of Jacobian JZW, which is equivalent to 1 by determinant of Jacobian xi yi. How we are replacing this ratio by these two determinants and what are their actual expression, it will be clear in next slide. For this, let us again consider that we have random variable z generated by using two random variable xy with functionality g, and for w the functional behavior is h. Let us say g1 and h1 will represent the inverse transformation, means from xy to z and w we can say g and h are forward transformation. Let us say g1 and h1 will be inverse transformation. It means if we have zw, by using g1 and h1 we can get the value of xi and yi. Now consider that delta z and delta w area that we have considered in previous slide, delta Z delta W area in ZW plane is given by this rectangle ABDC, where AB is delta Z and AC is delta W. Let us say this area in ZW plane is equivalent to the area of parallelogram A dash B dash D dash C dash in XY plane. And whenever this happens, we are, let us considering that the line A dash B dash will make angle phi with respect to x-axis, and line A dash C dash will make angle theta with respect to x-axis. And the area of this parallelogram is if equivalent to the area delta Z delta W in ZW plane, then definitely this area will automatically be equals to delta I. So if this happens, we can easily calculate area delta I as area of parallelogram A dash B dash this side into this side multiplied by sine of the angle between the two. Sine of the angle between the two will be this angle, that is theta minus phi. So A dash B dash into A dash C dash into sine theta minus phi. If we expand it by using the formula of sine A minus B, we will get this expression. Now this expression containing four terms, A dash B dash cos phi, A dash C dash sine theta, A dash B dash sine phi, and A dash C dash cos theta. Let us consider the first term, A dash B dash cos phi. This is the line A dash B dash, and if we take the A dash B dash cos phi, means actually we are taking the projection of this line along x-axis. So that can be determined as the differentiation of along x-axis, means the differentiation of g1 with respect to variable z multiplied by the area delta Z, that is this area. So A dash B dash cos phi will be del g1 by del z multiplied by area delta Z. Similarly, we can find A dash C dash sine theta as projection of this line along y-axis, and that will be del h1 by del w multiplied by delta w. On a similar note, we can determine A dash B dash sine phi and A dash C dash cos theta. So if we substitute all these four component value in the expression of delta I, we will get delta I equals to delta g1 by delta z delta h1 by delta w minus delta h1 by delta z delta g1 by delta w multiplied by delta z into delta w. This is del, this is delta. So delta I divided by delta z into delta w will be equals to this expression, del g1 by del z del h1 by del w minus del h1 by del z del g1 by del w, and this is nothing but the determinant of this 2 cross 2 matrix, del g1 by del z del g1 by del w del h1 by del z del h1 by del w. This determinant represent the absolute value of Jacobian JZW, means in that expression we have considered the absolute value of Jacobian JZW. This will be actually this determinant value, and this determinant value is nothing but the ratio delta I by delta Z into delta W, and this magnitude of Jacobian we have replaced in the place of delta I by delta Z into delta W. So delta I by delta Z into delta W, which is given by magnitude of Jacobian JZW, is actually having this determinant value. Similarly, we can say that the Jacobian JZW equals to 1 by magnitude of Jacobian JXIYI, where JXIY represent the original Jacobian transformation for Z equals to GXY, W equals to HXY, that is forward transformation. And in a similar manner, if we proceed, the expression of JXIYI will be calculated by this determinant at value x equals to xi and y equals to yi. Thus, the joint PDF of random variable zw, which was defined as summation over I joint PDF of random variable xy multiplied by del I del z delta I by delta z delta w, can be obtained as either this relation or by using this Jacobian this relation. So once we have the functional behavior is given and joint PDF of x y is given, we can easily determine the joint PDF of z and w. Now we are going to tackle two examples to elaborate this concept. Let us consider the example one is of linear transformation, where by using x and y, the random variable z is generated by using this linear relation, and similarly w by this linear relation. The a and b, c and d are constants. Now if ad minus bc not equals to 0, then the system ax plus by equals to z and cx plus dy equals to w has only one solution, and that solution will be given as x equals to sum capital Az plus capital Bw, y equals to capital Cx plus capital Dw. The expression of A, B, C and D you can easily determine by using this expression and this condition. Now if AD minus BC is not equals to 0, the same non-zero AD minus BC will be the Jacobian of x and y, and this you can easily determine by using this calculating del g by del x, del g by del y, del h by del x, del h by del y, and then calculating the value of this determinant. It will comes out as AD minus BC. So the joint PDF of zw will be equals to summation. Since we have got jxy, we have not got the jzw, so we will consider this expression summation over I 1 by magnitude of Jacobian jxy multiplied by PDF of xy, and simply substituting the value of jxy as AD minus BC, we get this quantity. And since there is only one solution exists, so the summation will cease because the value of I is only 1. So we have got AD minus 1 by AD minus BC multiplied by joint PDF of xy, but in terms of now z and w, because we want to find out this function in terms of z and w. So simply substituting fxy xy, x equals to az plus bw and y as cx plus dw, we get this expression. So this is a simpler example. Let us move to a slightly complex example. In second example, we have two random variables x and y. They are normal random variable, means Gaussian random variable, having zero mean and common variance sigma square. Along with they are independent to each other. So if this is happens, then fxy will equals to fx into fy because they are independent. So fxy equals to fx into fy. Both x and y are Gaussian random variable having zero mean and variance equals to sigma square. So their joint PDF fxy will be given as 1 by 2 pi sigma square e to the power minus x square plus y square by 2 sigma square, where x will equals to 1 by 2 pi sigma square e to the power minus x square by 2 sigma square. Now using these two random variable x and y, two other random variables r and theta will be generated by using these functions, that is r equals to root x square plus y square and theta equals to tan inverse of y by x, where theta is allowed to vary between minus pi to pi. If this is the given things and we have been asked to find out the joint distribution or joint density function of r theta and individual density functions of r and theta. It means we have been asked to find out fr theta and fr and f theta. So let us consider the function r equals to gxy equals to root x square plus y square, theta equals to hxy, which is given as tan inverse y by x. And if theta belongs to minus pi to pi, again this will have only one solution pair, and that solution pair will be x equals to r cos theta and y1 equals to r sin theta. So only one solution will exist. So for this, Jacobian jr theta will, which was defined as del x1 by del r, del x1 by del theta, del y1 by del r, del y1 by del theta, where we have replaced g1 function as x1, because in Jacobian we have defined del g1 by del z. So in place of g1 we replace x1, and in place of h1 we replace it by y1. So by doing so we get del x1 and del y1 terms. So if we consider that x1 equals to r cos theta and y1 equals to r sin theta, and if we calculate these partial differentiations, we will get Jacobian r theta equals to determinant of this one, and if you solve the determinant value it will come out as r. So we can say that magnitude of jr theta equals to r. With this information, the joint density function of r theta will be equals to, again summation will be ceased because there is only one possible solution exists. So multiplication of magnitude of Jacobian jr theta with the joint density function of x and y. So r into joint density function of fxy. Joint density function of fxy is already given by this expression, so we directly use there. You will get this expression as the joint density function of r theta, provided r is allowed to vary between 0 to infinity and theta is allowed to vary between minus pi to pi. From this joint density function we can get the individual density function frr if we integrate this joint density function with respect to theta for its entire range of theta. That is integration of joint density function with respect to theta for minus pi to pi. We will get this as expression as the individual density function of random variable r. Similarly, if we integrate joint density with respect to r for the range of r, that is 0 to infinity, we will get f theta theta equals to 1 by 2 pi. And if we see this expression and this expression, you can clearly conclude that joint density of r theta equals to multiplication of their individual densities. What it means? It means the random variable r and theta are independent random variable, and we are getting r and theta as independent random variable because it is generated by two random variables x and y which are independent. So if we use independent random variable to generate two other random variable, we also get independent random variable as the output. All the information you can easily get in this reference book by Papolish.